Hello, hello. Thank you so much for coming early. We're going to get started in about 7 minutes, 5 after the hour. So sit tight, grab some water, set up your workstations, all that. In the meantime, can I please get a quick, let's do a lowercase b. Wow, it won't let me type that. All right, uppercase or lowercase b for thumbs up. Then a D for thumbs down. Can I get a B that everybody can see and hear me all right? Cool. All right. Share my screen now that I know everything is working. And get that chat window pulled back up. Also, would love to know where everybody's calling in from. I'm in Austin, Texas, here in the US. Feel free to put it in the chat if you want. Oh, I just realized I'm only sending to hosts and panelists. Here we go. Denmark, Barcelona, Los Altos, Gig Harbor, Argentina, Nepal, San Francisco, Erie, Pennsylvania, San Diego. We are spread out. Tucson, Tunisia, Spain, Toronto, Germany. The Keys. Oh, cool. Jealous. Yeah, we are really spread out today. It's giving me a notification. Can I just really quick get another B that everybody can see the shared screen? It should say YOLOv8, start of the state-of-the-art data. Yeah, okay. Cool, thank you. Sorry, it threw up that notification, so I wanted to be sure. I also saw that people were calling in from the Philippines and Malaysia. That's cool. I love Malaysia. One of the best trips I've ever taken. If you're just joining us, we're going to get started in about 4 minutes. I just want to make sure that everybody has the chance to enter the room. In the meantime, feel free to share where you're calling in from in the chat. Would love to know. Hey. San Francisco, Maine, France. Another San Francisco, Portland, Italy. Yeah, we are spread out today. I saw South America, North America, Asia, Africa, and Europe. That's some global class here. I love it. Brazil. If you're just joining, we're going to get started in about 3 minutes. I just want to make sure that everybody has the chance to enter the room before I cover the beginning of this chat, because that's where I'm going to be giving out some of the important information for actually running the demo. So we'll give it another 3 minutes. Oh, yeah, and somebody from Norway. Cool. While we're waiting, here's a little preview of the demo. I'm just going to check on this training. It's going. So I'm doing this training on a A100 GPU, which is the most powerful single GPU offering we have, just to get like a much more complete version. I wanted to run it right during the duration of this webinar so that we would have just, something concrete to talk about. So that's all this is. You should be able to run everything on the free GPU, and I'll show you how to set that up when we get started. It's pretty easy. 2 more minutes. I see we got one more from France. Very cool. Excuse me. All right, just gonna give it 1 more minute here. Make sure. Seems like entrances are slowing down, but just want to be sure. Hello. All right, let's give it 30 more seconds. Last chance to grab water. This will be kind of an involved session. We're going to be moving pretty quickly, so just a heads up. Lots of material to cover. Okay. I think that we have filled up enough. Hello, everyone. My name is James, and welcome to today's Tech Talk. We're going to be talking today about YOLOv8 and state-of-the-art object detection models. If you're not familiar with us, we're from Paperspace Gradient. Gradient is a platform for scaling and building machine learning applications. You can explore a new library or data set in a notebook, automate your pre-processing, training, or testing of a model with a workflow, and bring your application to life with a deployment. I definitely encourage all of you to join our community of over 500,000 users on Gradient, but I suspect that if you're here, you are already. Before we get started, I would recommend that you all do this now, if possible. If you don't already have a Paperspace account, go ahead and make one. You'll be prompted to do that. Let me actually send out this link. Sorry. There we go. Now you all have the slides. And let me copy this. And oh, nope, it didn't actually copy. Excuse me. I'm just copying the link to this so that you can all jump right into the demo without having to do anything else. There we go. So you just need to click that second link to open up the demo. And all you need to do is create an account. This works on a free GPU, so you shouldn't need to create a paid one, and it all should be good to go. When you click on this, it will open you up into a window that looks like this. Just click Start Machine and Private Workspace to start it up once you've signed in. It should be easygoing. Oh, I'm not in presenter view anymore. Here we go. All right. So just making sure really quick, use the link here in the slides to log in and create your own version of the demo notebook. If you would rather not do that, I'm going to be running it as well, but that's how you can participate with me at the end of this session when we're going through the demo. All right, so without further ado, let's jump. Okay, David has pointed out in the chat something very important. There are over 60 of us in here right now. It's very likely that we are overloading the free GPU capacity. Everything that is in that notebook can be run without any changes or making any modifications. So you should be able to run this demo on your own later when the free GPU availability comes back up. I'm sorry about that inconvenience. If you would like to use a paid GPU, you can also follow along that way. But if you want to use the free ones, I'm sure they will become available after the end of this session. So for those of you who are unable to get the free GPU, my recommendation is just to try this later. It should be just as easy to run as with me walking through it. Thank you for pointing that out, David. Really appreciate that. If you have any questions or issues, please feel free to throw them in the chat, and I will do my best to address them as quickly as possible. If I'm on a roll, It may be a minute before I get to it. So if you need to re-put it in, go ahead and do that. I will more likely see the things that go in the Q&A than the chat, just for some clarification. Okay, let's launch into this because we have a lot to cover. So start off with an overview. We're going to start by talking about the intro to object detection. So just talking about what object detection is and some of the different approaches. Then we'll talk about the YOLO model itself, some of the history behind it, how it works under the hood, and the original YOLO architecture. We'll then jump into some of the newer YOLO architectures, specifically YOLOv8, and then comparing that with YOLOv8, talking about what's new in YOLOv8, and then we will jump into our code demo. Got another question in the chat. Can we clone this into our own workspace? So if I'm understanding you correctly, you should be able to put this into whatever workspace you want by clicking on the start machine, and then there'll be a drop down for whatever team or whatever team is the word, excuse me, team that you're in that you would like to put that in. If I'm not sure what else it could be for workspace. If you mean a specific project, okay, yeah, it only drops down when you click on it, so that must be why. Yeah, sorry for that. Good clarifying question. All right, let's jump into the intro to object detection. So this is we're going to start off with some layman terms, and then we're going to build into some really advanced breakdowns of the actual architecture. So bear with me if this is all familiar to you. In short, object detection is a computer technology that's related to computer vision and image processing that deals with detecting instances of semantic objects of a certain class. Think humans, buildings, cars, whatever sort of unique sort of object classification that we could give to some broad category of entities in digital images or videos. And down here, we've got some images. I believe this is from YOLOv8, showing some of the different classifications going on here. So we got cars, there's a bus, traffic light, people, handbag, all these sorts of things. Where in the original, well, actually not original, in the second version, which had some 82 different objects it could classify. That is still considered standard in when training from Coco. So you'll see these handbag, person, traffic light, bus, car in a lot of sample projects using YOLO. Object detection can be thought of as the union of two computer vision subdisciplines. These are object localization and object classification. Object localization is the ability to recognize multiple objects' positions in a single image, and image classification allows for the identification of the class labels for these objects. I saw that somebody raised their hand. Go ahead and throw something in the chat or do a Q&A question if you have something to ask, because I will not understand the hand raises. Next, image classification allows for the identification of the class label for these objects. And when you put them together, you are able to find the location and identify what type of object it is. This can be extended further into something that's called image segmentation, which is actually breaking apart those areas by what the object is occupying within the space. So I guess what total is being occluded by the object we are trying to watch would be image segmentation. Oh, my mouse is gone. There we go. Next, let's talk about some of the object detection approaches. Really, there are two sort of schools of object detection. Single-stage object detectors and two-stage object detectors. Single-stage object detectors treat image detection as a regression problem. So an image is input directly to the network, and then it outputs the class probabilities and bounding box coordinates, just one-to-one input output. Two-stage object detectors rely on the region proposal stage. So this stage identifies regions that could contain objects and then passes those on to the classifier for consideration. Single stage is generally faster, but two-stage before was considered generally more accurate. This is not really the case now, especially with YOLOv8 really kind of outperforming all of the competition. All right, so now that we've covered what object detection is, let's talk about YOLO itself. So YOLO was introduced in the paper You Only Look Once, Unified Real-Time Object Detection in 2015 by Joseph Redman et al. They devised a method for a single neural network to make predicted bounding boxes and class probabilities for objects on full images in one evaluation. Oh, I got a request for the slides again. One moment. Want to make sure I said that. All right, slides are in the chat. Sorry about that, Kelvin. Where was it? Ah, yes. So this is pretty much what I just said. The predicted bounding boxes and class probabilities for for objects on full images in one evaluation is pretty much exactly like that single stage object detection framework that we described a moment ago. And it really was the first approach to actually treat object detection as a regression problem. There's been a lot of advancement since its creation, and its successors have remained some of, if not the de facto top performant object detection models. And down here, I've got a little graphic from the original YOLO paper. This is pretty much the simplest way you can look at how YOLO works. So it processes the images in this simple and straightforward way where it resizes the input image to 448 by 448, runs the single convolutional network on the image, and thresholds the resulting detections by the model's confidence. So basically, it predicts a bunch of different object locations, and based on the confidence, it will output the ones that it's most confident on, in a nutshell. So getting into how this actually works. So like any supervised deep learning framework, the model requires labeled data to train on. And YOLO has some very, well, object detection models in general, YOLO in particular, has a very kind of, interesting and particular way of doing that. The tool I use for it is RoboFlow, and it allows you to directly label your images with the corresponding label and bounding box location. So we can see here in this GIF on the right, I labeled first this guy a ball handler, or no, sorry, player. And then the other fellow holding the ball is the ball handler, which I have to change by clicking there. This is the RoboFlow tool. It's since changed a bit. You can actually see here, it's gotten a little cleaner, but still basically the same functionality. So if we were doing something like adding in a new class, I could go over here, label the referee, and then put it in there. So it's a really useful tool for actually making your labeled data. The only problem is you have to manually do it. And considering this is only image 4 of 1089, it can become a pretty tedious and long process. So keep this in mind if you're going to be doing YOLO object detection work at any point. You're going to probably be spending most of your time doing that labeling. YOLO then learns during training to be able to predict the classification and bounding boxes of those objects. And the loss between the predictions and the real images during training allows the model to iteratively improve its predictions. So here on the right is an image again. I think this is from the original YOLO release. And let's just talk about what is really going on here when I say that it's kind of iteratively improving and identifying these bounding boxes. We haven't really talked about what's actually happening. So the way YOLO works to perform object detection in a single stage is it first separates the image into n grids. Each of these grids is equal in size S by S. So we have that, oh, I'm sorry, my mouse has vanished on me. Here we go. I have that here on the left. Each of these regions is used to detect and localize any objects they may contain. And for each grid, bounding box coordinates B for the potential objects are predicted with an object label and a probability score for the predicted object's presence. So we got these bounding boxes plus confidence here. As you may have guessed, this leads to a significant overlap of the predicted objects. You can see how much overlap there really is visualized here in this top image. To handle this redundancy and to reduce the predicted objects down to those of interest, YOLO uses something called non-maximal suppression to suppress all of the bounding boxes with comparatively lower probability scores. Using these probabilities and confidence values, YOLO is then able to narrow down the detected objects down to just those above the confidence threshold. And then these predictions are encoded as an S by S times B times 5 plus C tensor. So as we can see, we start off with a lot of different possible predictions. Then we have our class probabilities, and then only those that meet the threshold that we have predefined will actually be output as detected objects. Cool, cool. So that's how it works. Let's talk about the YOLO architecture. So under the hood, what is going on to make this possible? The YOLO model, the original YOLO model and all subsequent versions are made up of three key kind of subcomponents. These are the head, the neck, and the backbone. The backbone is the part of the network that is made up of the convolutional layers that detect the key features of an image and process them. Usually, this backbone is first trained on a classification data set, such as ImageNet, and is typically trained at a lower resolution than the final detection model, as detection requires finer details than classification. Next, the neck uses the features from the convolution layers in the backbone with fully connected layers to make predictions on the probabilities in the bounding box coordinates. The head is the final output layer of the network, which can be interchanged with other layers with the same input shape for transfer learning. So I wanted to really quick, I've got three different graphics that we're going to look at, and they kind of each increase in complexity, talking about YOLO here. So I wanted to go through each of these in the same way so that we can get a kind of robust understanding of how it works, both from a very coarse all the way up to a fine level. So we start off with this backbone that takes in the input and brings it down to these lower resolution versions. It then has a feature decoder which attempts to identify what features are in these spaces and outputs these predictions in bounding boxes. Then in the head, the actual prediction vectors are outputted and we get our specific values. And this version uses something called anchors. I'll talk about what anchors are in a little bit, but basically, in a nutshell, they are predetermined localizations that, rather than trying to predict the actual object centroid, it predicts the object's displacement from the anchor box. And this was the de facto methodology for most of the previous YOLO versions up until, I believe, YOLOv8. Okay, let's go into a little more detail here with YOLOv8. So YOLOv8 was the previous version of YOLO released by Ultralytics, which is the company that has released YOLOv8. YOLOv8 is the topic of interest for today. So it's pertinent to talk about what has changed from YOLOv8, in particular going into YOLOv8, to understand what the improvements that they've made are. So to start, we need to talk about YOLOv8 itself and the improvements they added. So YOLOv8 was the first PyTorch release, and it used a cross-stage partial network backbone with a path aggregation network for the neck. To go into some detail about what those are, a CSP net solves the problems of repeated gradient information in large-scale backbones and integrates the gradient changes in the feature map, which thereby decreases the parameters and floating point operations per second of the model, which not only increases the inference speed and accuracy, but also works to reduce the model size. Next, we have the path aggregation network, or PANet, which adopts a new feature pyramid network, commonly FPN, structure, which enhances the bottom-up path. This improves the propagation of low-level features. At the same time, adaptive feature pooling in the PANet, which links feature grids and at all feature levels, is used to make useful information in each feature level propagate directly to the following subnetwork. So PANet improves the utilization of accurate localization signals in lower layers, which can then be used to enhance the location accuracy for the object detection itself. Lots of words there, I know, but in a nutshell, these two changes work to increase the efficiency and the accuracy of the model overall significantly. In addition to that, in YOLOv8, all anchor boxes are computed automatically when you input custom data. So there's no more of that detecting the offset from the anchor box. Rather, it's going to the center of the automatically predicted object locations. This is a lot more robust. It also supports FP16 processing, which allowed for YOLOv8 to be trained in mixed precision for the first time, which is definitely a boon when it comes to training on particularly large image data sets. So here I've got, this is kind of just a new version of that same image we showed in the last slide. This is just having added more detail. So we got our backbone here, then the neck taking that, we have the backbone taking in the input, bringing it down to that lower resolution with the pooling, and then the PANet tries to propagate up these finer features to be predicted by the head. Cool. Oh, sorry, my dictionary just appeared. And finally, let's go really into depth. How is it making, I got a question. How is it making multiple BB predictions per grid point? Isn't there some sort of proposal mechanism happening there? My understanding is it's robust to occlusion and having objects both covered around each other. I can't remember exactly why. I'll have to get back to you on that, David. Sorry, I don't have an answer immediately. There is something. It is able to deal with occlusion, but I can't recall exactly what the mechanism is off the top of my head. Sorry. So in this one, we've got the YOLOv8 architecture. This is a really wonderful diagram from Range King, which is a GitHub user I recommend you all check out. He has some, or they have some really wonderful graphics for YOLO, kind of outlining everything that's going on under the hood with the architecture. And really quick, I see that there are more people who have just joined, so I'm just going to throw these slides in the chat. If you have not gotten the chat, I just put them in the slides. If you have not gotten the slides link, I just put them in the chat so you can follow along. All right. So as I was saying, this is from Range King. Definitely recommend you all check him out on GitHub. I'm sorry, that was microaggression. But this is the YOLOv8 model in much, much more detail. So let's walk through this. Yes, John Croker has spelled that completely correctly, like this. And if you are in the slides, they actually have hyperlinks in all of the images that look like this one. So there's one more with YOLOv8 that we'll talk about in a second. So you can get the direct links to each of these, as well as their analysis on what's going on, which I'm using as a resource for this conversation that we are having now. So definitely check out those links. They are embedded in the images. Okay, so the backbone extracts the features from the input. So we got an image of a cat here, and we've got these different pyramid networks, which are taking the features down. These are organized in feature pyramids by the feature pyramid networks in the neck. The feature pyramid networks are feature extractors that take a single scale image of an arbitrary size as input and outputs the proportionally sized feature maps at multiple levels in a fully convolutional fashion. The top-down pathway hallucinates higher resolution features by upsampling spatially coarser but semantically stronger feature maps from the higher pyramid levels. These features are then enhanced with features from the bottom-up pathway via lateral connections. Each lateral connection merges feature maps of the same spatial size from the bottom-up pathway and the top-down pathway. The bottom-up feature map is of lower-level semantics, but its activations are more accurately localized as it was subsampled fewer times. The final output is computed in the YOLO layer head. Oh, I'm so sorry. I just got a mild technical difficulty. 1 second. I lost my extra screen. There we go. Got it. Sorry. The final output is computed in the YOLO layer head and used to compute the cross entropy for classification, the L1 bounding box positions, and the objectness loss. So if we kind of look at both of these two diagrams, in this slide and the previous one, we can get an idea for how all those words I just said spell out. And by the way, if you have the slides, what I just said is in the discussion notes, so you should be able to read that. Don't worry about, I know that was quite a lot. So you will be able to read that out and then follow how it all goes up and through this process. But for the sake of time, I'm going to keep moving here. At the end of the session, we'll have some extra time, I suspect, so I'll go back to this. But I just want to make sure we have time to cover all of the YOLOv8 stuff, which we haven't gotten to yet. So finally, we've now seen the entire process for how YOLO works. We put it all together and we can see that the model is capable of detecting the presence and classification of the desired objects within the image data. So for this demo today, we're using NBA basketball footage. And as we can see from the example, the demo model is capable of discerning which player is holding the ball with pretty reasonable accuracy, I would say. Obviously, there's some moments where it's flashing out there. But we can see that the predictive accuracies, which are at the top of their name, are almost always above 0.7, which is reasonably high. And it's very rarely flashing to a non-ball handling player when they're not in possession of the ball. So this is just one of many potential use cases for YOLO. I was trying to think of something a little more out of the box with this one, rather than just, person, car, hot dog, not hot dog. But keep in mind that this is a super versatile model and you can use it for just about anything that you can label your image data separately with. Cool, cool, cool. Got my mouse. All right, now we are at YOLOv8. And I bet you that this diagram looks very familiar to most of you. So this is Range King's diagram for YOLOv8. Looks very, very similar to the other one, but there's some pretty significant differences if we start to dig deeper into it. To start off, they replaced the C3 module with the C2F module. So that is this module right here. C2F, I'll talk about what that does in a minute, but C3 module was previously in here, and they have replaced it with that C2F. Next, they replaced the first 6x6 conv module with a 3x3 conv in the backbone. So we go back and look here. It starts off with a k equals 6 at this top, and now we are at k equals 3. In addition, there were two deleted convs. These are number 10 and number 14 in the YOLOv8 config. So if we go back here, look on our right, we can see which ones were deleted. 8, 9, 10 and 14. So these two get the exact same functionality, if not better. And they replaced the first 1 by 1 conv with a 3 by 3 conv in the bottleneck. So that's these right here. The first in here, k equals 3. In the YOLOv8 is k equals 1. And finally, they used a decoupled head and deleted the objectness branch. So no longer are they also looking for objectness loss. Yes. I see that I have a question, and I'm going to cover a lot more detail about what I just said. That's just kind of the overview of the changes to the architecture. So I've got 2 questions I want to answer. Frames usually are highly correlated. Does YOLO have a special way to boost performance on predicting bounding boxes of the next frame, given the bounding boxes it predicted on the previous frame? My understanding is that no, it's not learning. It's not learning sequentially. I think it's just learning. So the way it works, I believe, is it's randomly looking at different portions of the images based on the way you've allocated the batches, and then predicting only for the labeled objects within those images within that specific batch. I imagine that some of the learnings within the batch probably are carried over, but I don't think that there's any kind of sequential learning, sort of like you would see in, like, I don't know, I'm trying to think of an example, like NLP stuff where you're predicting the next sequence or next token in a sequence. This isn't like that. This is more about looking at the cumulative objectness of each image. Next, was this in PyTorch instead of darknet? Yes, YOLOv8 and on are in PyTorch. In many applications, you can do moving average smoothing of the predicted bounding box. Okay, that makes sense. I haven't personally messed with that. That makes sense, though. Okay, let's dig into the nitty-gritty here a little more about what I just said. Thank you for the great questions and points, y'all. So, as I mentioned, they replaced the C3 module with the C2F module. This neck module is summarized by the picture on the right, where F is the number of features, E is the expansion rate, and CBS is a block composed of a conv, a batch norm, and a CLU later. In the neck, features are concatenated directly without forcing the same channel dimensions, and this reduces the parameters count and the overall size of the tensors. So in C2F, all of the outputs from the bottleneck, which are the two 3x3 convs with residual connections I mentioned we switched to, are concatenated. In C3, only the output of the last bottleneck was used. So the bottleneck is, so while the bottleneck is the same as in YOLOv8, the convolutional kernel size has changed from 1v1 to 3x3, and we've got this C2F to C3 change. I'm sorry, that kind of came out a little gibberishy there. Yeah. Go figure. So this is just a diagram showing the C2F module in the updated version of the YOLOv8 architecture. Moving on, earlier we mentioned anchor boxes and anchor box assignment. YOLOv8 was the first to not have anchor box assignment, but well, of the Ultralytics releases, that is. YOLOv8 also does that, but it has a new way of doing it. Really quick, let's talk about what anchor box assignment is, just to make sure that that's all clear. So YOLOv8 is an anchor-free model. That means that it's able to automatically detect the central point of an object rather than the object's offset from the center of the predefined anchor box for that region. Anchor boxes were considered pretty difficult to work with due to their bias towards the target boxes rather than the distribution being attributed to the actual custom data set. So by using anchor boxes, we're essentially introducing a sort of, I guess I would say it's explicit bias that affects the eventual outcome of the model training. So anchor-free detection reduces the number of box predictions overall, and gets rid of that bias, which leads to speeding up the non-maximum suppression, which is that complicated post-processing step that sifts through all those candidate detections after inference and removes those below the prediction threshold. So we can see that being demonstrated in the images on the right. But this is represented in the YOLOv8 and YOLOv8 architectures very, very differently. And that's why I included it here, despite them having sort of similar capabilities. So we see here on the left, the YOLOv8 head. Here, each of those different sort of, I guess I would call them channels, corresponds to that objectness loss, the L2 loss, and the prediction loss. They're then put together, concatenated to get that final output. YOLOv8 instead does this all in a single pathway and has deleted that objectness head. So it's really only got that split kind of down here at the bottom between the two. To be perfectly honest with you, they have not released the YOLOv8 paper, and I don't want to give bad information about what is really going on here to make the difference. So until that paper is released, I'm not going to make any more statements about this, but just know that there is a very significant difference that's represented in the architecture between how these automatic bounding boxes automatic anchor boxes are detected. Yeah. Finally, there is mosaic augmentation. So if any of you have worked with RoboFlow before, I'm sure that you've run into this term. But mosaic augmentation is basically the process of sort of sticking isn't the right word, stitching together would be better, component images from the training data, excuse me, together into composite images for training. So we're kind of supplementing the existing training data by combining the different images we have together. And we can see what that looks like in the image on the right, where we're taking all of the portions of these images that have the objects of interest, in this case, text. I'm guessing this is from an Arabic OCR application. And kind of stitches those all into one usable image. This is really useful in a lot of cases because it allows the model to recontextualize the localization of the predicted objects. What can happen, typically this is more of a problem for overtraining, is that you get all of your objects in some way. Let's say, we're detecting my water bottle here that I'm holding. Sorry, it's not very clear. If we're detecting that water bottle, but every single image of the water bottle has my face next to it, then the image is going to start associating the water bottle localization with my face being in that image. So by randomly stitching and moving around these areas of interest, we can augment the composite images to make a more robust training process that is kind of better at dealing with diverse backgrounds and noise. Interestingly, the researchers at YOLOv8 found that this is actually detrimental when used in the entire training process. So by stopping mosaic augmentation, their suggestion is 10 epochs early. I imagine it's actually pretty, it depends, on how much data you have, how many epochs you're training, and so on. So take that with a grain of salt. As a standard demo training run is 10 epochs. So if you are just doing the demo training that I set out, which is 10 epochs, then you won't even run into this. But they found that if they stop it around 10, it actually has a pretty significant effect on improving the YOLO prediction ability with the model itself. So pretty useful. When I did it myself, I think I got it went from like 0.62 MAP at 50 to 95 all the way up to like 0.657. So a 0.05 is pretty significant increase, and on a scale of 0 to 1. All right. Without further ado, we are now good to move on to the demo notebook. And for those of you who weren't there at the beginning, to open this up, all you need to do is click on that link here in the second to last slide. Then where it says Start Machine, go ahead and select whichever team space you would like to work in. Have an interesting question from Kelvin about mosaic data augmentation. Could we perhaps use the image-to-image tool? I'm guessing you mean like a stable diffusion image-to-image to do masking and object swap. Yeah, I'm certain if you wanted to make an artificial data set using your stable diffusion and image to image, very doable, very, very doable. Just, I don't know. I guess in the sense that you could do it automatically, that would be worthwhile. But I would suspect that doing just a more manual moving around of those objects of interest would actually probably be more effective, because image to image is going to distort whatever you put in there. I don't know. It's an interesting one. I imagine if your use case is something that's very well represented in the Leon 5B data set, then yes, that would work really well. Otherwise, not so much. Got another question. Okay, David, before I answer your question, I want to make sure everybody can do this. So once you've hit Start Machine, you should be taken to a page that looks like this. Well, actually, probably more like this. But click on the notebook.ipynb on the left and make sure that you install this. And then while that's happening, I will answer David's question. So how YOLO deals with the loss function of samples that maybe only have one bounding box versus samples that may have dozens of bounding boxes on it. Because the chance of having a big loss function in an image with more components is prone to exhibit more loss function than an image with one element on it. So you're talking about situations where a single object is represented multiple times in the image space, right? So sort of like going back here, it's like here where we have multiple cars. Can you confirm that that's what you're saying, David? Yes. So it's exactly like this. In a nutshell, my understanding is that it's able to do all of that processing simultaneously because of the way that it's a single stage detector. It's able to get everything from the feature map simultaneously. So all of the computations it's actually doing on the entire image space, not like focusing in on some small region. So it's not exponentially increasing the cost of doing the processing. That's my understanding. I may be wrong, but yeah. I hope that answers your question. If not, I will get back to it later. I just want to make sure that we all start this because we have 15 minutes left. Okay. Guys, do me a favor, don't steal my API key. For this next part, you are going to get the data set for this demo from RoboFlow. All you need to do is make a RoboFlow account. If you don't already have one, it's free to sign up. And then once you're in there, I believe you can just go into settings and I don't know. I'm not entirely positive where you get the API key from directly, but I do know that if you go to this link here, put in the chat, this is the data set if you want to take a look at it. I do know that you'll be able to get it if you are logged in and you hit export and then do show download code. And then your API key will be here in this blacked out section. So make sure that you get that API key so that you can actually download the data set from your own account. Like I said, it's free. Shouldn't take very long to sign up. And then you just paste it in here where that is, and then run this cell. What that'll do is it'll install RoboFlow and then get the all the data onto your notebook and then put it in this datasets folder here. Once that's done, and I've got my little demo here, which is slightly different than y'all's, we can move on to the train with YOLOv8 section. So we've already got our data all separated out, and we can look at it here in its splits. We've done some augmentations to kind of turn it around, make it a little more robust. Huh. I will get to y'all's questions in just a moment. I want to make sure that we just get to the run, just because it does actually take 12 minutes to run on a free GPU. So I want to make sure that everybody that is with us can do that. So I believe it'll say 8n here. So it's getting the YOLOv8n.yaml using the API. This new API is amazing, by the way. Ultralytics have really knocked it out of the park, made it super simple to use within a Python notebook. I definitely recommend everybody use the Pythonic methodology. So that's what we installed Ultralytics for earlier, and we're importing YOLO. We're specifically getting the weights for the YOLOv8n, which is the nano-sized or smallest model from that config. Then we are setting it to train. We're inputting our data here. RoboFlow will automatically make this configuration for our data for us. I believe it's set to 10 epochs, and default batch size, I believe, is 2. It might be 1. I'm running this on an A100, which is why I have much larger sizes here. So just leave it as is and hit run, and it should take about 12 minutes to finish, which will be right at the end of our session. Okay, now that that's going, really quick, I'll actually finish off just showing what this does. So finally, when our model is finished, we can input whatever, image we want by using model.predict here, and it will save to the runs detect predict folder. So let's do this. This will be predict 3 because it's my third one. Yeah, didn't really nail it. Okay. David and Jair, your higher user bin pip. So it sounds like the path to Python is missing for some reason. I suggest you just delete this machine and make a new one. I'm not sure what's up with that. Maybe contact support if you have the time, but that shouldn't be happening. Next, player and ball handler persons. There's a hierarchy to use this class in the learning. I don't personally use it as did I use this class in? No, I don't have a persons class that's kind of like a higher level one. I imagine that you can use this information for transfer learning still. And you should be able to adapt the existing net to have additional roles for players. I tried doing that. It's actually really hard. But I tried to get it to label like all the different guards, forwards, and referees, as well as who had the ball, as well as do a kind of a more general player. But I did find that within the same model, that would lead to some confusion. So it was better to stick to what is eminently clear as different. So if you were to have a kind of a higher order players class, that would not be immediately obvious to the model. Okay. Oh, RoboFlow is down. Sorry, y'all. Just give it a few minutes and then check again, I suppose. Sorry about that. If you do want to use my API key, I guess we can do that later. If it's still down, I can always change it, I suppose. Yes, I will be sharing this recording with everyone. Okay. So, okay, Jair, I'm so sorry if I'm mispronouncing it. I think you said you're from Brazil. No falo português. Pip install upgrade pip will solve that. Sounds like we have a deprecated version of pip or on this container. That will not actually interfere with any of the pip installs, but it will throw up an error. So that's why you're getting that. Sorry about that. Yeah, Thomas's suggestion works. So I have no idea why that was happening on yours, because it works completely fine on everybody else's. But if it does come up again, we can definitely work something out. That's definitely part of it. As Nick just said, the new version of pip was just released, so that's probably what you're seeing. Keep in mind, if you're using the pip 22 version and you're getting the error that says user bin pip not found, it is actually still working. Let me see if I actually have that error on mine. No, I don't. So I didn't actually do that upgrade and I'm not getting that error. So I'm not sure what's going on with y'all's use case. But pip upgrade pip will fix it if you don't like seeing that error message. Okay, going back here, we can see that this prediction from my model isn't that great on this image. Seems like I need to train it for a bit longer. Go figure. This is the third version, so I've got a few that work a little better, a few that work a little worse. It really depends how long you train it on, and for yeah, at only 10 epochs or only 50 epochs with very little data, it's not going to be that robust. So keep in mind, if you want this to actually work, you're going to have to extend the number of epochs pretty significantly. I also recommend increasing the batch size if you're not working on a free GPU. I think free GPUs can handle a batch size of 2, though, if I remember correctly. Next, I had a question about how this has improved. So here is actually the YOLOv8 repo. And this is currently the only place you can really find any information about how YOLOv8 improves on the previous versions. But here we can see from this graphic that each of the nano, small, medium, large, and extra large versions are outperforming the competitors in terms of mean average precision at both higher latency and regardless of the values and parameters and latency. So overall, much better performant, at least as far as their results have come so far. I'm actually going to be releasing a benchmark on this next week. So keep your eyes out for that next week. I'm going to be doing a direct benchmark using this data set, the Clash of Clans data set, and the aerial sheep data set, kind of extending our previous benchmark on YOLOv6 and YOLOv7 to YOLOv5 and YOLOv8. And we're going to be doing that across all sorts of different machines, single GPU and multi-GPU. So if you're trying to find the ideal YOLO and ideal price point, that will be the document for you when it comes out next week. Those of you who are able to get this training running, you should be nearing, I'd say it's probably like halfway point. It should be 3 minutes left-ish, if I had to guess. 3 or 4 epochs left. Thanks, Bruno. Have a good one. We're all done here, by the way, in terms of the actual content. So if you have any direct questions to ask, now is the time. If there's something I said I would go back to, definitely let me know. Okay. Franco asks, YOLOv8 prediction results are still different format than the YOLOv5, right? I wanted to add it to an existing pipeline and can make it work like YOLOv5, where I use results.panda.xy0. I don't actually know off the top of my head. That's a good question, Franco. My assumption would be that yes, they're the same. But I mean, I'm just looking at, so here we have our results. We can look at our results right here. This is what the output looks like for a prediction. So it's getting, looks like that final one is the tensor. So actually a 0 probably wouldn't work. I'm not really sure about this format. Let's see. Yeah, so -1 is actually the tensor. If that's what you were looking for, Franco. If that doesn't answer your question, feel free to ping again and I will have a look at it. So I got 2 more questions. Do I have comparison with other object detection? No, I haven't checked it against any of the others personally. I could add that into the benchmark if there's interest. But no, I think we can see in papers with code. Let's see. If you're not already on papers with code, this is a pretty wonderful aggregation website for finding out all of this stuff. So let's see, what are they using for this? And they have not released what their actual data is on. Let's see. Subtask, maybe. No. Let's see how I haven't checked on Paddle in some time. They tend to be pretty good as well. Okay, while this is translating, I'll answer the other question. My understanding is that there isn't a TF or JAX release yet. Okay, so the TensorFlow is coming, but it isn't there yet. And I don't see any mention of JAX yet. Seems like they're working in the Torch ecosystem rather than the JAX TF ecosystem. Which hardware configs did you use to train the base model for V8? Did you train it on any cloud? I'm not entirely sure what you mean, Gustavo. This was all done on the cloud here. This is a cloud gradient notebook. So for the demo that I sent to all of you, that was on a M4000 GPU. This one is on an A100 80 gigabyte. So I wasn't a part of the initial training. I can look it up in their repo though. Looks like they haven't. So the paper hasn't been released yet. I imagine we'll get more details about how this actually compares with other stuff, more information about the architecture. I know I want to understand how their anchor-free detection differs, for example. That really bothered me. It was hard to find. But yeah, currently there's no information about how their training process worked. Hey, thanks, Paul. Everybody, I think a bunch of people are going to have to leave now. Your model should be finishing now, so you can go on to that next cell and run that. Don't hash this out like I did, and you'll get your prediction on the sample image. You can input whatever image you want. Before we go, I want to call attention to the very last slide in the demo. That is super important. This is the link to the data set. Paperspace pricing link. So if you want to get a more powerful GPU, then we got the link to my repo for this article. Then we got the YOLOv8 original repo there. Got the original YOLO architecture breakdown. YOLOv8 Explained is a fantastic article from RoboFlow. This was my main resource for this presentation for the YOLOv8 sections, just because there is no paper out yet. Definitely recommend you all parse through that if you are interested in what's new and how it's changed. We've also got my blog post on YOLOv8. It's kind of very similar to what we talked about today, but if you wanted a written out version, this is where you can start. There's also the blog post on YOLOv7. And if you were lost in the CSP net and feature pyramids, so PA net section, I definitely recommend reading up on feature pyramids because they're complicated and interesting and can tell you quite a lot about what's going on. All right. I think we are all done here. I just want to make sure I answer these questions. Just making sure I'm getting everything. Yeah, Gustavo, I don't have an answer for that on the hardware config. If I had to guess, it's probably 8 times A100s. That seems to be the de facto methodology nowadays. I will be sending a recording out to everybody in the email. This will also go up on YouTube at Hello Paperspace is our YouTube channel. Yeah, thank you all very much. Okay, I'm not seeing any. Only just a few of the questions that I don't know how to answer. Sorry about that, y'all. Those who asked and I couldn't answer, but I'll definitely try and have an answer for you next time. Have a wonderful day, everybody. Have a great weekend. Good night. I understand it's probably evening for half of you. For those of you who are calling in at 3 a.m., you're champions. Thank you so much. Have a good weekend. And yeah, looking forward to seeing you all at the next one, where I will probably be talking about Val-E, the new audio impersonator model. It'll be scary, fun. Oh, all right, I'm going to end the presentation now. Goodbye, everybody. Thanks again.